Satellite observations reveal gaps in the infrared radiation that escapes to space at wavelengths characteristic of greenhouse gases, for example, carbon dioxide and methane. These molecules initially store the infrared energy in their vibrations, but collisions rapidly convert this into heat, warming the atmosphere. This natural effect, known as the greenhouse effect, was necessary for life to have evolved on Earth. Without it, the Earth's surface temperature would be a chilly -18 degrees Celsius. Since the Industrial Revolution, human activities have led to a rapid increase in the concentrations of greenhouse gases. Evidence from ice core records, and more recently from in situ measurements, show that CO2 levels at around 400 parts per million are higher now than they have been for over 1 million years. The average global temperature increased by approximately 1 degree over the last century. But how do we know this is linked to human activity and not down to natural variations in the sun's output or volcanic activity? Computer models indicate that there would have been a cooling from the occurrences of these natural events. And agreement with observed temperatures can only be achieved if the warming from greenhouse gases is included. So what is the role of chemistry in all of this? A single methane molecule is about 25 times more potent a greenhouse gas compared with CO2 because it is able to store more infrared energy. However, the hydroxyl radical OH, sometimes referred to as nature's detergent, is able to break the CH bond in methane, and so its concentration only builds up to about 1.7 parts per million. Overall, it causes less warming than CO2. In this satellite image of methane, you will notice that there is more in the northern hemisphere. This is because most methane emissions are found there, and its lifetime of about 9 years is not long enough for it to be mixed uniformly around the planet. OH is highly reactive as it contains an unpaired electron, with OH levels only reaching a fraction of a part per trillion, yet it controls the lifetime of virtually all species, emitted naturally or by human activities. It is therefore important to measure, but this represents a challenge as its lifetime is less than a second and it immediately is destroyed on any surface. During the last 20 years, researchers in my labs have measured OH all around the world using a sensitive laser-based technique. An instrumented shipping container, shown here at the Cape Verde Atmospheric Observatory, serves as our lab to measure OH on the ground, whilst the converted passenger jet aircraft enables OH to be recorded over large distances, providing an ideal target for model calculations.